So let's use the concept of area between polar curves to find the area of this green region, which is the area inside the circle r equals 2 cosine theta. That's that offset circle that I've described earlier, and outside the circle r equals 1. So that's just a circle of radius 1 with its center at the origin. So we draw two circles, both having a radius of 1, but they're kind of offset from each other, and we find this green region, and we want to understand it as the area between the purple curve and the blue curve. So let's find the area of that green region. First thing we need to do is we're going to need to understand that what we're doing is integrating through some angle, starting with this is going to be theta equals something, and this is going to be theta equals something else. So we have to find out what those are. Surprisingly, we do this by the same method that we would have used to find any other points of intersection. We simply set the two curves equal to each other and solve for the values that result in an intersection. So what we want to do is we have two curves, r equals 2 cosine theta and r equals 1. We're going to set them equal to each other and set 2 cosine theta. Get this a little higher up so I have more space. 2 cosine theta equals 1, or cosine theta equals 1/2. Now, let me just pause for a minute to ask why it is that this equation, 2 cosine theta equals 1, is going to give us the points of intersection. Notice that at this point of intersection and this point of intersection, we're looking for the same radius. Why? Because this point of intersection has some distance from the origin. We're looking for a point on the blue curve. We're looking for what angle we can plug into the blue curve that gives us a particular radius, such that if we plug in the same angle into the purple curve, we also get that radius. That means that if I pick this angle here and plug it into both curves, which by the way is very easy to do until r equals 1 because there's nothing to plug in, I'm plugging in the same angle into both curves and I'm getting the same radius, thereby generating the same polar point. It's going to be some point that looks like theta, comma, we know the radius has to be 1, so it's going to be some point that looks like that. So that's why this works. So I'm setting these two curves equal to each other. I've gotten to the point of cosine theta equals 1/2. We can see that cosine theta is going to equal 1/2 when theta is equal to plus or minus pi over 3. You should know enough about the unit circle to know that that's true. So okay, so those are the points of intersection. So what we can see is that I have theta is pi over 3 here and negative pi over 3 here. So there are the bounds of integration. Okay, so now let's set up the area. So the area is going to equal 1/2 times the integral from negative pi over 3 to pi over 3 of the outer curve squared minus the inner curve squared. Well, we can see that r equals cosine of 2 theta. This is the outer curve, and r equals 1 is the inner curve. How do you know? People often ask me that. I'm often puzzled by why that's a difficult problem, but let me just go over it briefly. If I draw a radial line out like this, look where I intersect first. I intersect the purple curve first, and then when I'm exiting the green region, the second point that I intersect is the blue curve. That tells me that the purple curve is giving the inside boundary, and the blue curve is giving the outer boundary. So this is one technique that you can use if you're confused about which is the inner curve and which is the outer curve, is start at the origin and draw a radial line outward from the origin. The first curve you intersect will be the inner curve. The second curve that you intersect will be the outer curve. So that's one way to think about it geometrically. All right, so we have now the outer curve, which is 2 cosine theta. So that's going to be 2, keep the same color here. This is going to be 2 cosine theta squared minus 1 squared. So in other words, I have the outer curve squared minus the inner curve squared d theta. And that's going to be 1/2 integral from negative pi over 3 to pi over 3 of 4 cosine squared theta minus 1 d theta. Now, one thing that you should recognize at this point is that this entire function here is even. In other words, we know that cosine is an even function. We know that constant functions are even functions. So if I plug in theta and negative theta, I get exactly the same values when I plug them into 4 cosine squared theta minus 1. So this is an even function, and I can simplify this a bit by doubling the integral and changing the lower limit to 0. Recall that from like really the very first lecture that we had. So this is going to be equal the integral from 0 to pi over 3. In other words, I change the bottom limit to 0 and I double the integral there, which removes that one, the factor of 1/2. So that's going to give me 4 cosine squared theta minus 1 d theta. Now, the antiderivative, cosine squared, recall that cosine squared of theta is, or I'll do it the same way I did in the previous example with a u. Cosine squared u equals 1 plus cosine of 2u over 2. So that's going to be 4 times 1 plus cosine 2 theta over 2. Oh, sorry, I'm still doing, I messed that up. I did the same mistake on the previous one. I haven't integrated yet, so I'm keeping the same functions until I've just converted the cosine into that expression. So that's going to be minus 1 d theta. Now we're ready to integrate. Actually, after one more simplification step, this is going to be 4 over 2 is 2, so this is going to be 2 plus 2 cosine 2 theta minus 1 d theta, which equals the integral from 0 to pi over 3 of 2 cosine 2 theta plus 1 d theta. Okay, so now finally we're ready to integrate. So this is going to become the integral from, sorry, this is where we find the antiderivative. The antiderivative of 2 cosine 2 theta is just sine of 2 theta. You can do that by u substitution if you want, but I think we're all familiar enough with the forms cosine ax and sine ax to be able to do that. So that's going to be sine of 2 theta plus theta going from 0 to pi over 3. We know that when we evaluate either sine of 2 theta or theta at 0, we're just going to get 0. So we simply plug in pi over 3. That gives us that's going to give us sine of 2 pi over 3 plus pi over 3, and then for good measure we'll put in minus sine of 0 plus 0. And that gives us the sine of 2 pi over 3 is root 3 over 2. And then, of course, we just have root 3, so we have root 3 over 2 plus pi over 3. And that is the area of this green region. Kind of inconvenient, but oh well. And this is how we do this. So what are the takeaways here? The main thing that I know is going to confuse people in this problem is two things. So these are the things you really want to focus on as you look at this example. Number one, how we found that we needed to integrate from negative pi over 3 to pi over 3. So just try to understand why the geometry is telling us that we set the two curves equal to each other and solve for the value of theta that makes them equal. That's what's going to give us the points of intersection. This is really the same thing as in an earlier example where I would have given you two curves where this is f of x and the blue one is g of x. How would we have found the bounds of integration? We would have simply set the two curves equal to each other and solved for a and b. So we're just doing the same thing here, but with the model of polar coordinates. The next thing that I know is going to confuse people is how we determined which was the inner curve and which was the outer curve. So try to understand this technique that I gave you, where you draw a radial line outward through the region, and that gives you, that's going to give you the first curve you intersect will be the inner curve, the second curve you intersect will be the outer curve.